So let's learn how to use the convolution method to solve a differential equation. So convolution method is a technique that we use under Laplace transform technique. So that means when you want to solve it using the convolution technique, the first step would be to take the Laplace transform of the whole equation. So let's do that. So taking the Laplace transform of both sides, we have from the first term s squared ys. So ys is the Laplace transform of yt is the solution, and then minus sy0 minus y prime 0. And then from the second term, we simply have a minus a ys. So ys is the same ys. And then on the other side, you can see it is a t. The first term is a t. So t means it is 1 over s squared. And if you are not familiar with these terms, you can find a common Laplace transform in the description. So you can study that first. Yeah, so t going to give you 1 over s squared uh, from the t term, and then 1 is 1 over s. So we have 1 over s. That's the second term. Yeah, so it's from 1. So you can find all of them in the table. And then what we do, we can actually do the algebra. We can simplify. We can take the common denominator. So there's always a question whether we do this or not. So normally when you try to use the convolution method, it's a good idea to simplify this one first, because you might see some nice simplification later. So that means if you take the common denominator, which is squared, so you can see it's going to be 1 plus s, so s plus 1. So that's what you get. Now what we do, we can substitute those initial conditions, and we know the y0 equals 0. That means this is gone to 0, and then it's also 0. So that means none of these terms will appear. That means you have a different technique, different simplification step if you have a some of those terms non-zero. So we can do that question in another video. So let's continue. So what happened now? We can isolate the ys term. That's how we do. That means we're going to factor out that. So that means you're going to get s squared minus 1 ys. So that's what we have on the left side. On the right side, we have s plus 1 over s squared. So the next common step is to divide both sides by this term. We're going to isolate ys. That's how we do next. So let's do that. So it's a ys. So if you divide, you can see it is 1 over s squared minus 1. And then we have s plus 1 over s squared. Now you can see, you can do some nice simplification. You can factor this term because of the difference of squares. You can do that. So you're going to get s minus 1, s plus 1. That's from the first term. And then we have the s plus 1 here over s squared, and you can see what happened. This term get cancelled out, so that's gonna simplify really well now. So that means what you get is we have 1 over s minus 1 times 1 over s squared. We can leave this as a product like that. Now you will see that the inverse Laplace transform of those two. So the first one has the inverse Laplace transform e to the t, and the second one has a t. So now, so you can see this is a product. Since we have a product, now we can use the convolution property. So what's the convolution property says that actually here we can use the uh, uh, idea that, so we have a product here. So when you have a product, what's going to happen is, you know that when you have a product of Laplace transform, when you go backward, the convolution theorem says it is the convolution of the those two functions. So let's just recall that idea now. So what we know by the convolution theorem, we know that, so if we define the convolution, let's say f times g function, two functions, we know that 0 to t f tau, and then g t minus tau and d tau. And then we also know that it doesn't matter which one we're going to put the t and which one we put the t minus tau. So what we normally do is we're going to put t minus tau so that it is easy to integrate. So that's just the basic idea. It doesn't matter which one. Now what the convolution theorem says, if this is the case, we know that if you take the Laplace transform of the convolution product, So what happened is simply going to give you the product of the Laplace transform is a product of the first one is the Fs, uh, Laplace transform for F, and then the Laplace transform of G. So that's what the convolution theorem says. So the first one is the convolution product. The second one is the regular product. So there are two different type of products. That's why we use it like a different notation here, star. So don't use the dot here, because I know some students try to use that, and that's not right. It's not the regular product. It's like a special product. And also you can write this one as, for simplicity, Fs Gs. Just the basic, just the multiplication. So now, because of that, if you try to get the inverse, what will happen? So if you take the inverse of the other side, inverse of Fs and Gs, that means a product, regular product, it's going to give you F star G, the convolution product. So that's the idea. So that's the convolution. So that means we just need to evaluate this convolution using the integral. So that's what happens. So now if you go back to the problem, so what we have here is we have in our problem we have ys is equals to 1 over s squared times 1 over s minus 1, and we know as we discussed before, we know that the first one is corresponding to t, the second one is corresponding to e to the t because of the first shifting property. So that means if you take the inverse, so yt is simply the inverse of that, because this is a product between those two functions. So by the convolution theorem, this is simply going to give you, you can say t convolution of et. So that's what happened. So it's in the convolution domain, that's the answer. So we're done with the convolution domain, but we normally don't leave the answer like that. What we do, we can use the definition, and we can integrate this one. So let's do that part. So that means you can use one of those versions, you know, that I told you, like you can, it doesn't matter which one you put the t minus tau. In this particular example, I'm going to give you, I'm going to put t minus tau for the first one. We'll see why. Because it's easy to integrate. So it is tau d tau. So we write it like that, and then we can evaluate this one. And also you can put to the other one and see whether the answer going to be the same. It should be. It doesn't matter. So let's evaluate this integral now. So we do that. So that means yt is equals to the integral 0 to t, t minus tau, and then e to the tau d tau. So what we do, we normally use a shortcut for these conversions. What shortcut is di method. So if you are not familiar with the di method, you can find the link in the description, so to learn that with some examples. So what we do, we normally put the first one, this one. The reason is when you take the derivative, simplify really well, and we leave the other one, integral one, e to the tau. So first take the derivative of the first one. Remember, here we take the derivative with respect to t, with respect to tau. That means t is a constant in this case. That means when you take the derivative, what will happen? You just get -1, because t is a constant, and the other one, integral, is e to the tau, no change. And you take the derivative again, you get a 0. So this is e to the tau. So that's the first step. And then what we do normally, we're going to multiply across the diagonal, put a plus sign for the first one. That's the idea. Minus. Okay, so that means it's going to give you the answer. Now what we do, we multiply across the diagonal and write the answer. So this is going to give you, the first one is simply t minus tau times e to the tau. That's the first term you get. The second term, you're going to multiply across the diagonal again, so you get negative, negative, positive. So you simply get e to the tau, and then we can evaluate this at t and 0. Now let's see what happened. When you plug in at t, you see if you plug in t for tau, the first term is 0. So second term going to give you e to the t. That's what happened from the first, when you plug in t. When you plug in 0, e to the tau is 1. And then the first term is going to give you t, and since it's the lower, you get a negative sign as well. That means a negative t, and the last one going to be -1. So that is the answer. So that's what you get as the answer to the problem, and you can see how well it works. But if you try to use the normal technique, which is the partial fraction method, and you will see it's really long. So let's write what happens if you do that. So so our fraction was this one. So it was 1 over s squared s minus 1, and which is identical to, make sure you write 3 lines here because we use properties of identity. So you can write equal sign, which is incorrect. So so the first term is going to give you a over s, and then we know by theory that even the squared term follow the same pattern. You can show that. That's how. So same pattern means this one. So it's a constant. And then you have 1 over not 1 c over s minus. So you have 3 unknown here. So you have to find all those 3 unknown. So it can take time to find those 3 unknown, because you can't just use get them quickly. So you have to use the hybrid method to get the answer. So yeah, so you can save a lot of time. You can completely avoid this finding partial fraction method using this idea. So this is how we use the convolution method to solve a differential equation really quickly. So you can see you get the answer very quickly. Okay, so I hope this helps you. So you can try like another problem. Yeah, so this is how we use the convolution method. Thank you.